Hi, this is the fourth YouTube video concerned with proportions and investigating them in SPSS, R, Commander and R. We're looking this time at two nominal variables which form a thing called a contingency table. More details at the website below. Here's an example of a contingency table. We have two nominal variables here. First, blood group O, AB, B and A, and also another nominal variable called severity of condition. The condition is either severe, mild or absent. You might class that as an ordinal variable, but in this instance, for this analysis, we're classing it as nominal data. So we have four categories in our blood type variable, and we have three categories in our severity of condition variable. We also have these values along the side, which are the marginal values, the totals for the columns and rows. This is an important aspect of contingency table because the word contingent or contingency means dependent upon, and a contingency table actually means we're assuming that the inner cell values are contingent upon the marginals. So we're saying that we can calculate our individual cell values from those totals. Full details provided in the PDF notes, and we'll just look at this example quickly. So here is this example, and take our first value here, which is 541. This is the expected value we think should occur in that cell, taken from the marginal values. So we just multiply the marginal values and then divide it by the total number. Obviously, if we can work out the expected values for each cell, we can compare the expected with the observed value. So we have here, for our first cell, blood group A, and the condition is absent, we have 143 observed cases, but we expect 141 if the inner cells are purely dependent upon these marginal values. The trouble is with these tables and all these numbers, I find it very difficult to understand what's going on. And I just like to quote these two sayings: if I can't picture it, I can't understand it. Albert Einstein. And getting information from a table is like extracting sunlight from a cucumber. So as I say, we've got these residual differences here, and we're back to the same situation we were before. The nice thing about these residuals or differences is that there's a value for each cell. This is in contrast to the chi-square statistic, which really we're just looking at usually is the cumulative value for the whole table. So we're losing a lot of information by just looking at the chi-square value, because if we look at the residuals, we actually see what's going on in the actual table, and we can see this graphically. So just to remind oneself about what the chi-square statistic is, we add up for all our cells the observed frequency minus the expected frequency. We square this so we don't need to consider plus and minuses of the residuals, and divide by the expected frequency. And this is equivalent to a measure of noise over signal. Again, detailed explanation in the notes. And this particular value, if the individual cells follow the marginal values we expect, follows a chi-square probability density function. But this only follows this probability density function as the sample sizes get larger and larger. We say it's asymptotic. That is, the actual chi-square value becomes more accurate as their sample size increases. And one particular problem is if we actually have an expected cell count of less than 5, we can't really say it does follow a chi-square distribution. It's just not accurate enough. And in that case, if we get an expected value of less than 5 in any cell, we need to use alternative methods of working out the p-value, which some statistical software gives us, like the exact p-value in SPSS that we've been using. Here is our data in SPSS. Notice that I have the labels marked So the value labels option is on, so we can see absent condition, mild condition, severe. If we click there, we can see the actual values I typed in. So we can see we've got A, B, AB and O blood groups, and for each of those we have the category absent, mild and severe, and then our count variable. Just looking at the variable view quickly, there are 3 value labels for condition. There are 4 categories, value labels for blood type. And there's our count variable. Notice I have to find those as nominal. Going back to the data view, obviously the first thing we've got to make sure that we've done is weight the cases to count. Select count as our frequency variable, weight cases by count. The first thing I'd like to do is actually graph the data to understand what's going on. So go to graphs, legacy dialogues, bar, and then we simply choose stacked. So that is graphs, legacy dialogues, bar charts, stacked, summaries of groups of cases, and click the define button. Now we set this up in the usual manner with condition as a category and blood type as the stacks. So we're going to have the category which is mild, absent, severe. So we'll have 3 bars, and each of those will be stacked by the different blood group types. And we're getting the numbers in each one. Okay, and there is a result. Again, what we want to see is the actual proportion in each condition. So to do that, we just open the chart editor by double clicking on it. Then options, scale to 100%. Now we can see for each condition the proportion in each blood group. And what we're doing with the chi-square test here, before we just, remember, looked at one frequency and it took the average frequency for that one value when we had the dichotomous variable. Now we have each variable has several categories. What it's doing is taking the overall average of each of these blood group types and saying, right, we expect for each condition them to have the same overall distribution of blood group types. So you can see that severe have a higher than expected probably number of B-type blood, and mild, particularly low type. The trouble with this type of bar chart is it's not giving any idea of the actual proportion of weighting we need to give to each of these conditions or blood types. You can either have it showing the proportion of blood type, or we can have it other way around and showing for condition. We can't have it showing overall the relationship, and we're going to look at another way of creating that in a minute. Before we look at a better way of graphing the data, we'll just carry out the chi-square test very quickly in SPSS. There's 2 ways of carrying the chi-square test, both from the analyze menu. The first option is to go to non-parametric tests, legacy dialogues, chi-square. The problem with that approach is that you can't ask for various options in the cells. You can't ask for residuals and expected values, etc., etc. Alternative is to go to Analyze Descriptive Statistics, crosstabs. Analyze Descriptive Statistics, crosstabs, and that's what I'm going to choose now. OK, and then we're going to put in condition for the row and the blood type for column. If we look in exact option, we'll choose the exact version rather than the asymptotic version. P-value. OK, continue. Look at statistics next. Obviously we want chi-square. We'll also choose this thing here that says contingency coefficient. I'll explain that later. Contingency coefficient, press continue. Cells, we can ask obviously for the observed value. That's chosen by default. We can ask for expected value, and we can ask for standardized residuals. can also ask for a thing called adjusted standardized. This is because standardized residuals don't actually follow exactly the standard normal distribution that we've talked about. And click continue there. Don't need to worry about formatting or bootstrapped. Click OK. After a while we get our results. It may take some time considering I asked for an exact p-value and we've got 1,500 cases. Possibly I should have stuck with the asymptotic version in this instance. Anyway, here we are, here are results, and we don't actually have any expected cells that are less than 5, else it would give us a warning. And we've got 5.3, which is heading that way, but nothing below 5. And we can see the standardized residuals for all the cells, it's quite small, the largest one is minus 1.1, so very unlikely to have a significant chi-square value, and that's what we also thought from looking at the bar chart, if you remember beginning. So here are the actual chi-square value. Just look at the exact values here and we can see they're all 0.5. And we notice there's no difference between the asymptotic version of the chi-square 0.529 and the exact version, which is 0.53, 1/100th difference. And here's this value here, which I asked for, contingency coefficient. I'll mention that again later on. So, given our p-value here, we conclude that 53 times out of 100 we would obtain a table like this, or something that's more extreme in terms of a chi-square value, given that it was based upon just the marginal values. That is, that you could fill each cell up from these marginal values, and that means that both variables we say are independent, which means that the proportions for each category is not different. So the proportions of absent, mild and severe are the same as the overall average for that variable condition, and similarly the blood type proportions do not vary between A, O, B and AB. I would like to introduce you to another free package that you can load into R called VCD. Right, and you can see here it's to do with visualizing categorical data. This website's extremely good, by the way, for information about this, and we're going to create a mosaic plot and an association plot for our data set, and we'll see what these are when we've done it. So as usual, we've got to download this package, this free package, and then use it in R. So here we use the standard command install.packages, the name of the package VCD, all lowercase, and then we say dependencies equal true. So the other packages it needs that we haven't got on our system, install them automatically. Press return. Ask us where to get the package from. Choose UK, London if you're close to it. That's it, it's downloaded. So to use the VCD package, we just type in library bracket VCD close bracket. It's told us it's loaded required packages as well. So here we have the VCD library loaded, and we can see a table down there. It's quite a complicated process this to use the mosaic plot and the association plot. So I'm going to begin by defining my data, and I want to define my data in the form of a table, or actually in this instance it's not so much a table as a matrix, which is equivalent to a table. So here we are, we have the data, and what we've done is make it into a matrix. We concatenated these values together, all these values you can see here. 543 is first row, first column, 44 first column, second row, 28 first column, third row, etc. So we've done it column 1, then column 2, then column 3, then column 4. We've told R we've got 3 columns and 4 columns. That's what makes up this data. You'll notice that I've left it in limbo. This is deliberate because I want to continue on the next line. I could write this all on one line and carry on, but I'm just going to press continue now, and it automatically adds a plus sign in. It knows that there's something more to come before it finishes the command. And now I'm going to specify some names for the columns and the rows. So I used a thing called dim names, which it understands as part of matrix, and it says the names consist of a list, first condition, which consists of 3 values, and then blood group, which consists of 4 values. So basically those 3 belong to that, the rows and the 4 columns are there. You could have specified it columns then rows rather than rows and columns, but you've got to make sure you get them in sync, as it were. So once we've done that, we can see what we've got in the data. There we are, exactly as we wanted. 543, 44, 28, 211, 22, 9. It's always a good idea to check this because you can get them wrong quite easily. Right, to draw our association plot, a mosaic plot, we just use a command that's available via the VCD library. So it's ASSOC, then put our data in, then main, remember, means title in our language, so we're going to give it a title. We want some shading in. You can have it just so it shows all the blocks we'll see empty, but it's actually quite nice and shaded. So we press return and we should get a graph. There we are. Enlarge it. So here we can see for our conditions, absent, mild and severe, and for our blood groups, you see the dotted line, that's represented as the expected value, and these are the Pearson residuals. It's showing that for absent, it's very slightly above that you imagined. For blood group B, it's slightly below. For blood group AB, it's slightly below as well. And for O, it's slightly above. The only 2 that really stand out are condition mild, blood group B, and condition mild, blood group O, which is below that expected. But you'll notice here that, as I say, the value is quite low. It also gives us p-value there. With this data set, nothing really deviates from that expected to a large amount. If it did, the colours would change, and I'll show you one at the end with different colours where this happens. Closing that window, now we can ask for a mosaic plot. So what we've just done there is analyse the residuals. Now we're going to be looking at the values in terms of how they relate to one another. So now open the graphics window. There we are. So we've got, it's not very good at formatting R, this is usually the problem. We have absent, mild and severe there, and then the blood groups here. So now you can see, not as you can with the bar chart, you can see relative areas equaling the proportions of each. So you can see that blood group A and blood group O have the largest number of patients, and B and AB particularly have smaller percentages of patients. Similarly, we can see that the largest proportions are to do with the absent condition in all 3, and then the mild and severe far fewer, and severe even fewer. Again, if there was important differences, these would be coloured differently, and I'll show you one in a second. I think these mosaic plots are extremely useful in seeing what's happening. Looking quickly at my PDF document, Proportions and Chi-square, and going to section 6, Residual Analysis, Association and Mosaic Plots, you'll find at the bottom of the page some more examples of mosaic plots where I've doctored the data slightly, and you'll see that I've changed the data there. I've made one of the groups quite significantly different from the others. One there, and you'll notice, and there's another value I've changed earlier on to counterbalance it. So here, that's the original association plot, and there's the one with the doctor data, where you can see that the p-values are drastically changed. It's 9 zeros in front of that, and then we can see that it shows us which are the values that go to +4, which are the values that go to -4. So that's very different from what's expected, and that's very different in the other direction. On the following page, we expect if there's a differences displayed in the association plot, we'd expect for the mosaic plot there would also be these differences shown. So we can see there that that's way beyond expected for the severe blood group A, much larger, and in the other direction that's much smaller, blood group O. I hope this helps you understand what's going on with the chi-square, and also how you can use a graphical interpretation of tables. So to carry out the chi-square test in R, it's pretty much the same as we did in the last example with the one-way classification. Now we have a result which we get from the chi-square.test using the data we defined before. Type in result and we get the values. Chi-square value 5.11, p-value 0.529, and if we type in the result $residual, we get the Pearson residuals for each cell, and if we type in result $expected, we get the expected values for each cell. In our command, it's pretty much the same as before as well. We go to statistics, contingency tables, enter and analyze two-way table. So that's statistics, contingency tables, enter and analyze two-way table. Then we can put it in either way around, it doesn't matter. So we'll go for 4 columns and 3 rows. Once we've entered the data, we can choose what we want. So we want column percentages and chi-square test of independence. And we can ask for print expected frequencies as well. Click OK. And there are the results. Column percentages. Counts of the table, just to check. And chi-square value, degrees of freedom, p-value. Expected values we asked for as well. So in this 4th YouTube presentation concerning proportions and chi-square, we've got on to the 5th aspect that we're going to consider of our 7 or 8. We've looked at single proportions, we've looked at several independent proportions, we've looked at the goodness of fit approach, and now today we looked at 2 nominal variables and contingency tables. We looked at why they were called contingency tables, and we carried out the analysis both SPSS, R Commander and R. Remember, we had 2 nominal variables, but they might have actually been ordinal variables, and we decided to consider them as nominal data in this instance. We specifically, besides looking for the chi-square value and its significance, we also looked at association plots which showed us the Pearson residuals and the deviation from what was expected, and if this deviation was important, then different coloured shading that appeared. Similarly, we looked at mosaic plots which showed the relative proportions for each cell, and again the deviation was shown by shading. Both these plots really are a form of residual analysis, quite similar if you think about it to the regression analysis we carried out. The next YouTube video will be looking at paired data and Mcnemar's test.